Hello everyone, I'm Neha Bisht from Department of Ocean Engineering and Naval Architecture, IIT Kharagpur, India. Today I'm going to present my work on flexural gravity wave motion over multiple sinusoidal seabeds. The co-author of my work are Pavan Negi and Professor Trilochan Sahu. The outlines of my presentation are its introduction to the triads and flexural gravity waves, its objectives, mathematical formulation, evolution equation, results and discussions, conclusion, and its references. Introduction to resonance. Resonance occurs when a wave strikes an object which is vibrating with a particular frequency, and the frequency of the wave matches with the frequency of the object. Triad resonance. When the two propagating waves with wave number K1 and K2 interacts to give a wave number K3, implies omega 3 is equals to omega 1 plus minus omega 2, such that K3 omega 3 satisfies the dispersion relation, then this interaction is known as triad resonance. The objectives of my work is to analyze the resonating interaction of flexural gravity waves with sinusoidal beds of finite length. Here, the evolution equation for flexural gravity wave motion in a homogeneous fluid with amplitude sinusoidal seabed is derived. The role of detuned frequency on Bragg scattering of flexural gravity waves due to various physical parameters such as plate rigidity, compressive force, number of undulated sinusoidal patches, and plate thickness is investigated. Basic assumption and schematic diagram. Here the fluid is considered to be inviscid and incompressible. The flow is considered to be a rotational motion, is simple harmonic in time with frequency omega. The floating elastic plate is modeled using the Euler-Bernoulli beam equation with the inclusion of lateral compressive force. The mathematical model is formulated using linear water wave theory and small amplitude structural response. Here we can see this is the plate covered surface. This is the rigid bottom bed. This is the sinusoidal bed of patch length L, which is described by delta X. Mathematical formulation. The governing equation is given by this. The linearized kinematic boundary condition on the plate covered surface is given by this. Euler-Bernoulli beam equation in the presence of lateral compressive force is given by this, where P external is given by this. Linearized dynamic boundary condition on the mean plate covered surface is given by this. And the combined, hence by combining dynamic and kinematic boundary condition, we get the linearized plate covered boundary condition as this. The undulated bed profile delta X defined by this, where L is the wave number of the, small L is the wave number of the undulated seabed. The bottom bed kinematic boundary condition is given by this. Introducing the slow variables, multiple scale expansion method. Introducing the slow variables, x bar is equals to epsilon x and t bar is equals to epsilon t. Phi can be defined as this, where phi j is equals to is a function of x, t, x bar, t bar, and z. So using the perturbation method, we can see the first order problem will be the homogeneous problem. And the second problem is the inhomogeneous problem in the function of phi1. Now using the method used in my 1985, the first order potential phi1 is obtained as this, where psi plus minus are vertical profiles of incident and reflected waves, and given by this a plus a minus are the amplitude of the incident and reflected waves. The dispersion relation is given by this. The second order problem using phi1 as described earlier. The second order problem will be given by this. The boundary condition is this. and the bottom bed boundary condition is this. Now for the resonance to occur, L will be equals to 2K. Hence we can see when L is equals to 2K, the flexural gravity incident wave K1 omega 1 as K comma omega interacts with the sinusoidal seabed K2 omega 2 as 2K comma 0 will give us the resonating reflected wave K3 omega 3 is equals to minus K comma omega, which satisfies the triad condition K1 minus K2 equals to 3 and K omega 1 minus omega 2 is equals to omega 3. Now, considering phi 2 to be in the form of this is this, hence the second order problem becomes this. From here, we can derive the evolution equation as this, where a plus a minus is associated with the vertical functions psi plus psi minus, and Cg is the group velocity. Neglecting the inertial force gamma omega square, the group velocity and cutoff frequency omega naught is given by this. Now omitting the overbars from x comma t and changing a plus to a and b minus to b. The evolution equation for the n patches is given by this. This is the schematic diagram for the n patches. Here we can see this is the length L1 and this is the gap length small L1. So for the gap and the x less than 0 and x greater than x any, the evolution equation will be like this. Now, considering the wave number to be slightly detuned due to the Bragg resonance with wave number this and detuning frequency as this, the solution will be of this form for the patch. Now, using the matrix transform method, the solution of the evolution equation are obtained as this, where the reflection and transmission coefficients are given by this, and H1, Sj, Mj, Tj, and Hi are defined by this. Here we are validating our work with the work the work published by May 1985 and the Houston 2015. We can see this is the variation graph of reflection coefficient with the with S, which is omega naught L by Cg, with the variation in the length, which is very well validated here. For E equals to 0, Q is 0, T is equals to 8.5, H equals to 10, and the amplitude of the sinusoidal seabed D equals to 1. And here for the Houston, the variation is with the detuned wave number for various values of S. Similarly, we are going to plot the reflection coefficient versus S, which is omega naught L by Cg. This is the reflection coefficient, and this is the graph of the transmission coefficient. The variation of the reflected wave intensity over the sandbars is plotted here as a function of omega naught L by Cg for varying rigidity of the plate, with Q is equals to 0.5 root D, keeping other parameters constant. It can be seen that below the cutoff frequency for E equals to 0 and E is equals to 6 into 10 to the power 7, the variation is monotonic, and above the cutoff frequency, here the variation is oscillatory. So we can see that as the As E increases, the ratio omega by omega naught is also increasing, hence resulting in the oscillatory pattern. Now this is the reflection coefficient versus S for the varying compressive force Q. Similarly, here we can see as we increase Q, the ratio is always less than the cutoff frequency. Here we can see that this is always less than 1. Hence, the graph is always monotonic and attaining the complete reflection. Here we are plotting the variation with the varying plate thickness. We can see, and we are keeping E as this and Q as this. We can see that as the plate thickness is increasing, the ratio of omega by omega naught is also increasing, hence resulting in the oscillatory pattern. Similarly, when the number of patches are increasing, we can see the ratio is constant, but the graph is attaining the monotonicity for the smaller values of S also. Here we are plotting the reflection coefficient versus the detuned frequency for varying E. As the E is changing, the value of S is also changing, where S is omega naught L by Cg. And we can see as here, we can see as E is increasing, S is decreasing. Hence, we can see for the smaller values of E, we can attain a full reflection. But as E is decreasing, we are not able to attain the full reflection. Now, as this is the reflection coefficient versus omega by omega naught for varying compressive value, we can see as Q is increasing, S is also increasing, hence attaining the complete reflection. Conclusion, the ratio omega by omega naught increases as the rigidity of the elastic plate increases, whereas omega by omega naught decreases as the value of compressive force increase. The ratio omega by omega naught increases as the thickness of the plate increases, whereas omega by omega naught remains constant as the number of patches increases. Whereas in the case of uh, where we have plotted the KR versus the detuned wave frequency, we can see as the rigidity of the plate increases, the value of the S is decreasing, and as the compressive force increases, the value of the S is increasing. These are my references. Thank you.